first of all, we have to remember this, right? Do you remember this notation? Summation sigma means summation notation. And so this is a condensed way of writing the sum of a certain pattern. So if I said, like, this is just very theoretical, I wrote one out like this, where I said k equals 1 to 5 of 3k, it just means you start at this number, you end at this number, and you plug in 1 to n for each one of those values. 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. So the condensed version of that is using summation notation. You can kind of think about, as we do more rectangles, every time when you do RAM, whether it's LRAM, MRAM, or RRAM, you're doing the sum, right? Like, you do the same thing each time because you just plug the heights in. So kind of like on the one we just did, you could say start at k equals 0, end at 2, and then whatever your function happened to be. Well, not really, because we were going by like 1 or whatever. But anyway, kind of that idea of adding up a bunch of stuff. It's easier to use summation notation. You're not really going to be doing summation notation, but I just want to show you that this is going to come up in our proof, and so I just wanted to remind you of that there. And then when we do these sums, when we add these rectangles up, instead of calling it RAM, rectangular approximation method, kind of the more accepted word in calculus is to say a Riemann sum. And I'm really bad. I always want to say, I always spell it wrong. I never know if it's I-E or E-I. I struggle. And it's, I forget the guy's first name. Oh, George, there's no E at the end. Okay. He died in 1866. I agree exclusively with this existence was not established mathematically until George Riemann proved this in 1851. And so RAM, people used RAM way before good old George came along, but George is the one that proved what we're going to talk about today, and so that's why we call these Riemann sums. I will tell you on the AP test, they say use a left Riemann sum, or use a right Riemann sum, the midpoint Riemann sum, more than they say RAM. And so interchangeable. So we're going to talk about this. What if we want to make these rectangles like 500 rectangles or 1,000 rectangles, or and what if we didn't have a calculator? And that's what we're going to do. So I drew this lovely graph for you. So let's say that f of x is a defined function on a closed interval. That's defined continuous. And then I should make you write all this. I don't have to write any of this. What if we break this up into n subintervals by choosing n-1 points, such that we're going to pick numbers in between a and b, and I'm just going to label them starting at x1. So like if I picked a point here, I broke it up as x1, I picked another point, that would be x2, and I would keep going to x to the n-1. Because think about if you wanted 4 rectangles, you could only have 3. So all of those are between A and B. And obviously I haven't picked a lot up here. There could be infinitely x values in between. I need this to be like changed around so that all this hot air is cold. So we want to think about what would the width and the height if we made these into rectangles. So it's like between A and x sub 1, and between x sub 1 and x sub 2, and on and on and on. If I made those into rectangles, what would the width and what would the height be? They're not going to be numbers, right? You have to kind of think here for a minute. Oh, I feel like you shouldn't see them. Really, really fast one. There's one that we talked about. Oh, Matt. But math pickup lines and one time together in real time. It's always the last day. Then there was one that was really appropriate and it said, okay, I'm not going to say this out loud, but this heard it to my sister well. And she had cracked up laughing and my father not tell me that. And I was like, wait. There's some that are very sneaky. There's one I'll show you. It's not super appropriate, but it's sneaky and appropriate, and I almost put up a picture. So, like, I totally would get it back. And, you know, well, that's funny because it's using that. So, okay, sorry. I want to make sure I use the right notation so that it all fits together here. So I had to find a little bit here. Do you agree that the width is going to change depending on how many values I have in here? Right? The more subintervals I have, the smaller the width is. Yes? So just arbitrarily, I'm going to call it the change in x sub k. Where's the k? Where x sub k is just this, right? Like x sub y can't do x sub 3, right? And then the height's going to be dependent on, one, what the function is, right? So that's what you have to plug into the function to get the height. And then the height's going to depend on what each one of these are, right? At x sub 1, the height would be whatever f of x sub 1 happens to be. And at x sub 7, the height would be at whatever f of x sub 7 would be. So k's are like arbitrary values. So we're going to say that the height is just f of why do they it's very inappropriate to write. And they did do it. Oh, look at your book on page 275. Can you reload the book again instead of me? At the top of page 275, you can kind of see where that x sub k comes into play. Right? So it says like between a and x sub 1, the width would be the change in x sub 1. And the width between x sub 1 and x sub 2 would be the change in x sub 2. So then they just pick some value in between there. So let's go through x sub 1, and this is x sub 2, and this just keeps going. Somewhere between there, they just call that x sub k minus 1. And they have an x sub k here. And then it says each subinterval will be split sub some number. Note the number chosen from the k subinterval by c sub k. So because we're over here, we're choosing some number and they change it to c sub k instead of x sub k. Again, we're just kind of trying to do a proof here. You're not really going to use this after today. I just want to show you where it comes from. And this book kind of goes into a little more detail, and I can read into more of the look here. And again, nice and big here, you can see that this could be a negative number because my graph is very nice and it's all positive. But if my graph goes and it dips underneath here, that height might be a negative number because the height might be a negative y value when you get here. If we add all these rectangles up, that's kind of what we want to talk about here. If I add all these rectangles up, I'm going to use a summation. All right, so I'm going to say the summation, I'm going to use a sigma. And very nice, because we're using k, it's going to make sense here. That I can say where k equals 1. And remember that n is the number of subintervals, the number of rectangles. So at the top, I'm going to say from 1 to n. And remember what we're doing. We're finding the area of each rectangle. How do we find the area of each rectangle? How do you find the area of any rectangle? Length times width. Or we're going to say width times height. But yes, just take those two numbers together. So I'm going to write it. I'm going to do the height first. I'm going to say that's f of c sub k. So that's my height every time. Times the change in x sub k. This is exactly what we did with LRAM, InRAM, and RRAM. We just didn't do it so we just said we had 7 rectangles. This is a proof, and the proof shows that this works for no matter how many rectangles you take. So whether it was 100 or 1,000 or a million, and that was before they had a program that could do it for them. But this is kind of the notation of how to do that. And this is where this idea of an integral, which is kind of what we're talking about, comes from. All right, so take this, go to the next page. This is pretty small. As the partitions of A to B get smaller and smaller, so as my width gets smaller and smaller, what's going to happen to my approximation? Does that make sense? Like, as those widths get smaller and smaller and smaller, you look at the picture on 275, think about that white space that's not counted right now. Like, that's going to keep these smaller and smaller. It gets more and more accurate. The rectangles become more and more accurate. And we can say that all Riemann sums for a given function on A to B converge. That's what converge means. Like if we took the limit as the number of rectangles go to infinity. Or another way to think about that is the limit as the width goes to 0, right? So another way to think about it as the limit as the change in x sub k goes to 0, right? Because if the width goes to 0, then it's going to converge. They converge to a common value called the definite interval. Yesterday, when you did your program and you got LRAM, InRAM, and RRAM to like be the same number, and I told you that that was like the exact value of the curve, we were finding the value of the integral using the computer. And just like we can talk about derivatives and all the properties of those, we can also talk about integrals. And we can say that if you have a continuous function, it will always be integrable. There's a new vocab word for you, right? So like in calculus, like integrable. So what we want to talk about is the notation. We want to say exactly the 500 rectangles. use that as notation for intervals. Okay, so that's why I want you to know that word. So, if a function is continuous on a closed interval, then a definite interval over that exists. It's the area under that curve, and here's your notation. It makes like an elongated S like this. Your book talks about, I find it very interesting to read about, is it says the Greek letters have become Roman letters, meaning that they take that summation, and it's kind of a stretch to think about, but if you stretched out that summation, do you see kind of how that looks the same? I don't know. I don't think I'm on the integral. You can see the difference. I know, I'm sorry. You gotta do this first. The limit, as n approaches infinity, it equals that s. I just forgot to show this. Of the summation a n of our f by c sub a times g. Now we say we're writing f. That's the whole reason, so that we can have this. So then, where each c sub k is chosen arbitrarily and dictates something. Okay, we want to change this, and that's where I jumped. We want to change this to the notation that we're going to use for integrals, and maybe I'll just come back to this. I'll just say that. So, the definite integral of a continuous function, if you partition it into n subintervals, then your change of x, I don't know if you don't know this or not, if you realize this, your change of x, how wide each one is always b minus a over n. If you look at the programs that I wrote, like that's a line that gets something that each rectangle is, or you can just draw it out and think about it. And so the definite integral we're going to just write it again, right? Where each c sub k is arbitrarily in the case. We're going to change it to our and that's the same as if we change it to this Roman S, which I'll show you. Oh, look, here's the notation when I use this when I type it. So you can see mine's not as good as this, right? Maybe I always strive to make it. And the more I do it, the lazier I get. It just looks like a regular S. Then curve the bottom. And so instead of having to worry about from A to B in terms of like typing in the interval, in a definite interval you put A at the bottom and B at the top. And then when you have a function, instead of having to say how many rectangles do I have, if we talk about the number of rectangles going to infinity, we can say that this is the same as just f of x. And if you remember back when we first talked about derivatives, change of x, right? If you think about slope, change of y over change of x, like that just means delta, like delta x means change in, and we changed that to dy over dx into the change of y over the change of x. So this just changes to dx in our notation. And I'm going to rewrite this part down here so I can tell you what all these parts are called. Alright, so I'm going to write a little bit. called an integral sign. Yes, it is just a Roman letter, I think. But in calculus, we call it an integral sign. And your a to b are just, it's just your interval. So this is called lower bound or lower limit of integration. And this is really upper limit. And this is like the interval of b. And then f of x is just a function, which means if we're talking about rectangles, it's just a function that you graph. In integral speak, f of x is called the integrand, like what you're taking the integral of. Not. Just like you have the divisor and the dividend when you divide something. And then this dx is called the constant of integration. Which means that, again, depending on what you're doing, it might change. If your equation is with respect to s, this would say ds instead of dx. If it's talking about velocity and it's written in terms of time, that would say dt, because instead of dx. So that tells you, like, whatever this letter is next to the d, it's like with respect to x, with respect to y, with respect to x. And so that is where that comes from. So when you see this whole mess here, it is read as the integral from a to b of f of x with respect to x. When you find the value of the integral, you've evaluated the integral, maybe more importantly, you found the exact area under that curve. Not the approximation, the exact area. It's pretty cool that they did this and went in 4 times. So today, we're not actually going to find the exact area because we don't have the exact area. But we're just going to practice going from this notation to this notation. So let's think about it before we go into an example here. But notice that this summation just turns to the integral sign. Whatever the a to b happens to be, that just goes on top of the bottom. And instead of f of c sub k, it's just whatever the equation happens to be. And then this just changes to d whatever. Which means your homework, really, you could probably do in like 5 minutes today, because it's just kind of looking at the notation. And then tomorrow we'll get into more of actually like finding it. So this is what your homework looks like today. It says express each limit as a definite integral. Kind of maybe notice the difference between how I wrote it and how they wrote it. Because they didn't write f of c sub k. They just got the function written in there. But notice that c sub k is just changing to x here. So on this one, again, the limit part goes away because we're not taking the limit anymore. Just as when we did the definition of a derivative, the definition comes from the idea of a limit, but then when you actually just take derivatives, you don't have to limit anymore, like it's in the process. So this just becomes the integral from 1 to 2. And then instead of 2c sub k, what's that c sub k going to change to? Oh look, I think that's true to x. Yeah, I think that's big change. So that's just going to change to 2x. And then your change of x sub k is just dx. And that's an integral. That's the answer. We're just changing. Evaluating it. Doing the rectangle. So try the second. That's the whole function. 3c sub k squared minus 2c sub k. What case is Right, and so really that dx is supposed to go to everything, so that's a good question. So when you do this from 3 to 7, 3x squared minus 2x plus 1, really all of that's the integrator. So you see how they have in parentheses. Technically, that's how you should write it. We always talk about this at conferences, like, what if they don't put the parentheses around it? Is that wrong? What, if it was a question where you had to write it out, and it depends on the situation, and as we get into this more, we'll talk about it, but for now, try to be accurate in that, yes, if there's more than one thing added or subtracted, you should put in parentheses to say that that's all with respect to x. So you only have 1 through 6, which are all doing this, which means that you should all get this done before you go on, okay? But again, sometimes I think it's worthwhile to kind of go through the proof. If you want to read your book, I try to shorten it as much as possible, which is one of my mistakes. But it really goes into a lot more detail in your book if you want to look at this subject of and tomorrow, we will get into a value integral without having to use our calculator, without having to use random. So, you'll need
I'm excited to see Bradley's